So now that we have finished the timing diagram for only J1 and K1, our first flip-flop on multisim, let's see how we now incorporate the second flip-flop. So we base the second flip-flop, J2 and K2, off of Q1 and not Q1 of the first flip-flop. And I can see that right here on my schematic. J2 and K2 are based off of Q1 and not Q1 respectively. So let's attempt to work through this problem and see how this shift register comes into play. So when J is 0 and when K is 1, when J is 0, K is 1, Q is 0. So Q1 is always going to be 0 anywhere that J1 is 0. So let's draw that border. Anywhere that J1 is 0, J2 is also going to be 0. Now at this trigger, at this purple line right here, J1 went to 1. However, this J2 is dependent on the output of J1. J1 is still technically 0 on this vertical purple line. It's transitioning from 0 to 1, but it is not 1 yet. It's in the transition state, so we're going to treat it as 0. Because of that, this distance between this purple line and this purple line forces J to remain 0. Now, at this vertical purple line, at this next negative trigger of my clock, going from high to low, J is 1 and K is 0. Because J is 1 and K is 0, J is 1, K is 0, Q becomes 1. So Q1 becomes 1. Okay, let's do that up until the next purple line, which is right here. Well, J1 is still 1 here. It has to be. It's in the transition state again from now 1 to 0, but it has not transitioned to 0 yet. It's about to. Because of that, J2, my Q1 output, remains 1. Now at this vertical purple line, J1 is 0. K1 is 1. J1 is 0. K1 is 1. Q becomes 0. So to repeat this and to start from the very beginning, I found J and K1 based on my clock signal and my data. I am now going to use the output of J1 and K1 to be my inputs for J2 and K2, which I can see on the schematic again. I have to look at what is the value of J at the given time of the clock. If it is in transition, if it is transitioning from 1 to 0 or from 0 to 1, I'm going to use whatever value it started with. So here, J is 0. At this clock trigger, it's transitioning from 0 to 1, but it's still 0. So that means Q1 is still 0. Here, right here, it transitioned already. It became 0 earlier. Here it is 0. So that means that Q1 becomes 0. And we follow that over to the next purple line. The next purple line is right here. Well, J1 is 0 at this purple line. Because J1 is 0 at this purple line, Q1 is 0. And that happens until the next negative trigger, which is right here. I know I don't have the purple lines, but it is right here. At this trigger, the negative trigger of my clock, J is 1, so Q becomes 1, and so on and so forth. And by now, you should see a pattern. Oops, didn't mean to put that one there. Notice, it is the same exact wave as J1, but it's been shifted over by one clock trigger. And that's the point. It has to be. Because it is a shift register. That's where that word comes into play. Now, how do we figure out K2? Well, K2 is just the opposite of J2. So whatever J2 is, flip it. Anywhere that J2 is a 0, make K2 a 1. Anywhere that J2 is a 1, make K2 a 0. And you'll end up with the same exact pattern as down below with J1 and K1, the same exact pattern here, except shifted over. Let's see how that affects J3 and K3. So looking at our schematic, J3 and JK3 is this flip-flop here. J3 is dependent on Q2. K3, I know it doesn't say a 3 here, but it does down below. K3 is dependent on Q not 2. So it's dependent on whatever these guys were, whatever their output is our input for J3 and K3. So let's look at that as we work through this. I'm going to stay zoomed out so that we can see our clock signal here. So J3, we're only looking at J, and we're looking at what was the output of JK2. Well, at this point, from here to here, this point right here, J was 0, K was 1, so Q is 0. So J3 is 0. J still 0, J still 0, J still 0, J still 0. J went to 1 here. However, J is still 0 on this negative trigger. It is not 1 yet. It is transitioning from 0 to 1, but it is not there yet. Because of that, for the next trigger period from this purple line to this purple line, J3 is still 0. Now, at this purple line between I and J, these dots right here that I'm moving my mouse up and down on, J is 1. J2 is 1. Because J2 is 1, J3 also becomes 1. And it follows that until the next trigger. Well, that next trigger is right here between K and L, which I'm highlighting with my mouse again. But again, J2 was a 1 here. At this point in time, J2 is still 1. So J3 is like, great, you're still 1, I'm continuing on until the next trigger. J3 becomes 0. And notice it's the same exact pattern, just shifted over ever so slightly. And that's how I'm able to fill out this table. Remember, K3 is the opposite of whatever J3 is. And I know that because it's Q and not Q. Whatever Q is, not Q is the opposite. So let's draw in K now. It's the same exact pattern as the previous two setups, the previous two J's and K's. The only difference here is it's shifted over again to the right. So what do you think that's going to do to J4 and K4? Well, J4 and K4, this last flip-flop, are dependent on J3 and K3. So whatever J3 and K3 are, that's going to affect J4 and K4. J3 is 0 all the way up to here, so I know at least J4 is going to be 0 all the way up to there. Now here, my clock triggered. It's a negative edge trigger. My clock sent a signal and said, hey, look at me, I'm doing something. But J was 0 here, so J4 remains 0 until the next clock trigger. At the next clock trigger, J3 is 1, so J4 is 1. And it's the same exact pattern as before. And lastly, K4 is the opposite of J4. So I'm going to draw that in without going over an extra line. And this is what our timing diagram ends up looking like. Now I want to do one final thing. I'm going to erase my purple lines because I think it'll be a little beneficial to see everything without these markers in the way. And you should be able to see the pattern very clearly once I get rid of all these purple lines. Here we are. The black lines down here are my clock and my switch controlling the data. That switch is at the very beginning over here, this switch. The red lines are my signals. Notice they are the exact same, except they're offset from one another. I'm going to mimic that in the simulation right now. I'm going to stop it and restart it, and I'm going to clear everything out. Now, I said that for 2 clock toggles, for 1, 2, from high to low 2 times, D is doing nothing. So D is doing nothing. Then D goes high for 2 clock toggles. So 2 clock toggles. There's 1, there's 2. And then D goes low again for 2 more clock toggles. 1, 2. And then D goes high again. 1, 2. Notice what's happening to my light up there. It's almost like it's scrolling across the screen. It's shifting from left to right. This is the timing diagram using the circuit. Instead of this, I am just using these flip-flops to shift it from start to end. That is all that is occurring here. It's just looking at my data, looking at my inputs versus my outputs and how they control one another. It's like a game of telephone. If I'm talking to Mr. Davidson in a game of telephone and his goal is to get the message to Mr. Stallings, but he has to go through Mr. Bolin and Mr. Bolin has to go through Mr. Strand and then Mr. Strand can tell it to Mr. Stallings, I can't directly tell Mr. Stallings my message. I have to start with me, JK1. And then I tell that to Davidson, JK2. And he tells that to Bolin, JK3. And then Bolin tells that to Strand, JK4. And then JK4 tells it to Mr. Stallings, JK5. So it offsets. It's not an instantaneous thing. It's passing it on. It's a relay in a race. You cannot just jump from start to finish. You have to go from one to the next, to the next, to the next. Now that's only half of this activity. If I look at this activity, your goal is to build this and simulate it. The second half of the activity is understanding that your rightmost JK flip-flop is your most significant binary digit, and your leftmost JK flip-flop is your least significant binary digit. And that's important to answer the question of why is the number D, or the letter D, the number D, the letter D causing this output down here? Well, we know D in binary is, let's see, 9, A is 10, B is 11, C is 12, D is 13 in binary, and you can see that in the start of the activity as well. 1101 is 13 is D. Well, if I wanted that to be an output, I have to say whatever the binary number 1101 is, to represent the letter D, that is what my logic needs to be. When 1 is on, and when 1 is on, and when 0 is off, and when 1 is on, 1101, give me my output. So your activity says to make necessary modifications so that the circuit will detect an input sequence for the number 7 in binary. Well, if we have 4 bits, this is 2 to the first, or I'm sorry, 2 to the 0, 2 to the first, 2 to the second, 2 to the third. 2 to the third is 8, so this should be a 0. So I have 0 and 1 and 1 and 1, because 111 in binary is the number 7. That's all part 3 is asking you. It's asking, what is this logic going to look like? So that only when the number 7 is displayed here is this probe lit up. That is your goal with this activity. I know these videos were a little long and it can be overwhelming. Take it one step at a time. Understand one flip-flop at a time before moving on to the next. Don't try and move through them all at the same time. That is not sequential logic. Sequential logic says, what the heck's going on here? Okay, what the heck's going on here? Okay, what's going on here? And lastly, what's going on here? In order from left to right. Good luck. I have office hours throughout the week, and you may also email me at any given time for any questions about these activities. Have a great day, guys.